we're going to keep going with inverse trig functions, so now we're going to talk about the inverse of cosine of x. So here's a rough sketch of the y equals cosine of x graph. And we want to restrict the domain so that we actually have an inverse. Because clearly this graph does not pass the horizontal line test, so we don't have an inverse to start with, so we must restrict the domain. So the standard place to restrict the domain of cosine of x is from 0 to pi. Remember, we need a domain where the range covers the whole range of the original function, so here from -1 to 1, and also we need, when we restrict the domain, to then have an invertible function that passes the horizontal line test. If we look at what we have here, we have an always decreasing function, and it does in fact pass the horizontal line test, and the range is from -1 to 1. So here we have y equals cosine of x, and if we restrict the domain, we get from 0 to pi, and our range is from -1 to 1. In our inverse function, we call it arcsine or cosine inverse of x, just like with the inverse of sine, we had arcsine and sine inverse. They both meant the same thing. These two mean the same thing. You should be able to go back and forth between arc cosine of x and cosine inverse of x. And by back and forth, just recognize that they mean the same thing. The domain here is from -1 to 1. Remember, this is a ratio of the adjacent side over the hypotenuse, or you think of it as an x-coordinate. That's what that is. Okay, while the range of arc cosine is from 0 to pi, this is always an angle, and it's an angle in radians. So let's do an example. We want to evaluate arc cosine of -1/2. Now, where is the range of arc cosine? We want to think about what we're trying to find. -1/2 here, that's a ratio of the opposite side over the hypotenuse, or it's an x-coordinate. And then the output is going to be an angle, and that angle needs to be between 0 and pi, so somewhere in either the first or second quadrants. So since arc cosine is negative, that means really we're going to end up over here in the second quadrant. Oh, I don't need to do that. Okay, so you might recognize this number here as one of our special triangles. If you remember, if I have a special triangle of I have 1, 2, and this third side is square root of 3. This angle here is pi over 3. Okay, which means that I would have this angle here, and that would be pi over 3, which means that this angle, which is the one we're looking for, is going to be pi minus pi over 3, which is 2 pi over 3. How did I get pi minus? I got pi minus because this whole angle is pi, and I wanted to subtract off the pi over 3, and so I ended up with pi minus pi over 3. Oh, I need to erase all of those, which is 2 pi over 3. Okay. So let's do one more. Let's evaluate sine of arc cosine of 1/4. So this is a little bit more involved. We're going to find arc cosine of 1/4 and then take sine of that. So we have this 1/4 arc cosine is going to take a value in either the first or second quadrant, and since 1/4 is positive, it's going to be in the first quadrant. So arc cosine gives an angle, and there it is. Okay, if I draw that ray in the unit circle, I can think of this as a right triangle. Remember, this is the unit circle, so this piece has a radius of 1, so that's the hypotenuse of our triangle. And since we know cosine of this angle is 1/4, we know that this horizontal side measures 1/4. That is the x-coordinate of that point. And what we really want to know is, what is the y-coordinate of that point? Well, we can use the Pythagorean theorem. And we get square root of 15 over 4. So that is sine of arc cosine of 1/4. Alternatively, you could have just thought about this as the triangle. Remember that arc cosine is going to give you an angle in the first quadrant, and so that means that sine is going to be positive at that angle. And I could have taken this triangle to be 1/4 if this is my angle. And then this last side would have been square root of 15. So again, the sine of this angle is going to be square root of 15 divided by 4.